Greetings to you. Let us continue our discussion on the accessories of spectrophotometer that includes fluorescence and phosphorescence spectrophotometry. Yesterday I have given a small brief introduction to fluorescence and phosphorescence phenomenon. Basically fluorescence phenomenon is approximately equivalent to spectrophotometry, but phosphorescence there are no phosphorescence measurements cannot be accessed through an accessory as a spectrophotometer. You have to have a dedicated instrument for phosphorescence, but for fluorescence there is an accessory is available. But even though accessory is available nowadays, yesterday I informed you that the fluorescence phenomenon studies and requirements in instrumentation and other things have necessitated the development of fluorescence spectrometry as a science of its own. Therefore, even though accessory is available, you can also choose a dedicated fluorescence spectrophotometer. So, let us see what is fluorescence. Now, I hope you remember that our discussion about electromagnetic radiation, how it is absorbed by a molecule, and the absorption phenomenon is accompanied by the reduction in the intensity of the incident light, that is absorption. And sometimes what happens is if the solution is not clear, then there will be scattering, turbidence, nephelometric phenomenon and all those things, reflection, refraction and refraction. All these things will be taking place, and one of them is fluorescence. So, in fluorescence what happens is electromagnetic radiation absorbed by a molecule in a given solution is sometimes re-emitted at a re-emitted. If the this is known as luminescence. In this process, photons of the electromagnetic radiation are absorbed by the molecules and then excite them to higher energy level, and when the excited molecule returns to the ground state, the molecules luminesce. This phenomenon is known as photoluminescence also, which includes both fluorescence and phosphorescence. So, we can define electromagnetic radiation as absorbed by a molecule either through photoluminescence method technique or through simple, you can call it luminescence also. Now, fluorescence occurs in a time span of about 10⁻⁻⁵ seconds, as the excited molecules are short lived. In general, absorption takes place in about 10⁻⁻15 seconds. Compared to that, fluorescence is quite a slow process, which takes place in about 10⁻⁻⁵ seconds, and phosphorescence takes much more time. It may extend even up to a few minutes. So, phosphorescence involves a change in the electronic spin, and hence it is a physical phenomena. It has to be much slower than the fluorescence. The lifetime of the excited species in phosphorescence also extends from 10⁻⁻several seconds -4 seconds to several seconds, sometimes even minutes. So, this is the main difference between fluorescence and phosphorescence phenomena. In photoluminescence process, emission occurs at the wavelengths longer than the excitation radiation. Now, here you have to understand that whenever we talk of fluorescence, we talk of two wavelengths, electromagnetic radiation of two different energies and two different wavelengths, because when the molecule absorbs part of the radiation, and if the radiation that is coming out is of different wavelength, then the incident light we call it as the excitation wavelength, and the radiation that comes out is called as emission. So, emission radiation. So, obviously, if part of the energy is absorbed by the molecules, the energy of the outcoming radiation would be definitely much lower than the incident light. So, if the energy is lower, the wavelength should be longer. It is a simple phenomena which we have discussed number of times. Now, this is the schematic presentation of the absorption phenomena, absorption, fluorescence and phosphorescence. So, here what happens is most of the molecules are in the ground state, and the many of the ground state energy states are occupied by the electrons in S0 state. Here I have the excited state S2, S1 and T2. I will come back to you why I call them S2, S1 and T2, and here I have to take you to the fundamentals of absorption phenomenon, and whenever the energy is supplied in the to the molecule in a spectrophotometer, what happens is the electrons absorb the radiation and go to the next higher energy level. And as I have told you earlier, the energy absorbed is released through several vibrational and rotational energy levels and comes back to the ground state of the excited energy level, which I have shown as a bold line here. From here the return will be to the ground state, any one of these states, but mostly populated on the bold line which I have drawn at the bottom nearest 0. So, in the absorption phenomena you can see that the energy is simply absorbed and the output is having an energy less than the incident energy. Now, here what happens in this case, this is internal conversion, and if the electrons lose their extra energy to come back to S1, and then from here obviously the wavelength, this much energy is absorbed and lost, and the corresponding energy when it is emitted will result in an electromagnetic radiation that is having a longer wavelength. So, the electrons molecules can come back to the ground state at different energy levels also, and the most populated energy level is the one which will show you a fluorescence peak. So, fluorescence phenomena is determined like this. Now, you can see I have also drawn one more system where the bold line in the third type is I have designated as T2, and internal and external conversions. What happens is from here the energy there is one more stable energy level which is not exactly an excited energy level, that is electronic energy level, but slightly lower, and but having a definite energy, corresponding energy. So, the molecules will not only come to S1 in this case as in fluorescence, but they proceed further down to T2, and then the emission occurs at different wavelengths just like fluorescence. So, obviously, this is known as a metastable state, and also there are a lot of intersystem crossings, and it may lose the energy, absorbed molecules may lose the energy to other solvent molecules and their own molecules by collision and other things. But still basically the fluorescence, phosphorescence and absorbance phenomena are represented like this, and it is easy to understand for us how these processes take place. So, fluorescence occurs or in what kind of substances? We can see the fluorescence. We can see fluorescence in gaseous substances, liquid substances and solid chemicals also. For example, if you remember your street lights containing sodium, the sodium lights will be emitting radiation around 589 and 589.6 nanometers. Here the sodium vapor absorbs 3s electrons of the sodium vapor. Vapor means basically element. So, the electrons get excited to 3p state, that is the energy state, and after about 10 raised to minus 8 seconds the electrons return to the ground state while emitting radiation at the same wavelength in all directions. This type of fluorescence, where excitation and emission occur at the same wavelength, is called resonance fluorescence, and many molecular species emit at radiations at longer wavelengths than the excitation wavelength. This is called as Stokes shift. So, longer wavelength means Stokes shift, and this is the schematic representation, and electrons are paired here, and then one electron is excited to next higher energy level. This is known as excited singlet state. And then if the spins are opposite, then it is known as singlet. If the spins are parallel in the excited state as well as in the ground state, then it is known as triplet state. So, this is a bit unnatural, but therefore, triplet state would be having an energy still lower than that. So, molecular absorption, as I explained to you, occurs around 10 raised to minus 5 seconds. Excited singlet molar state occurs with an average lifetime of 10 raised to minus 5 to minus 10, quite often around 10 raised to minus 8. So, this has a minimum average lifetime of about 10 raised to minus 4 seconds minimum. So, otherwise you may not see any fluorescence. So, the properties of the excited singlet state and triplet state differ significantly from each other. This is understood, easily understood. So, radiation induced excitation of the ground singlet state has a low probability of occurrence for triplet state, as this is a forbidden transition. Most of the triplet states are forbidden transitions. So, even though there is a theoretical possibility for the excitation to occur, the intensity of the triplet state, the population intensity of the triplet state spectrum, or the population of the triplet state by the electrons is somewhat lower only. Therefore, when both processes occur in the same molecule, fluorescence and phosphorescence, phosphorescence wavelengths are much more longer than fluorescence wavelengths. For example, in typical systems you may say about 10 to 20 nanometers as excitation and fluorescence difference, that is excitation may be at emission wavelength will be about 30 nanometer longer than the excitation wavelength, 20, 30, maximum 50 like that, but it will not be much higher than that. But in phosphorescence, because it is a forbidden transition, concentrations are lower, concentration of electron in the triplet state is lower. So, it will occur at much longer wavelengths. This phenomenon you should understand, and we will see other typical phenomenon in this case also. So, what are the theoretical aspects of the fluorescence molecule, fluorescing molecule? An excited molecule can also return to its ground state by other radiation-less processes. That means, apart from emitting a radiation, it will lose a part of its extra energy by these methods. One is vibrational relaxations. I think all of you remember that every excited electron electronic state is associated with a several number of vibrational and rotational energy levels. So, I have shown you earlier also in one of the slides that vibrational relaxations do occur in the schematic diagram, and then sometimes what happens is internal conversions. This also I have shown you in the same figure, and sometimes external conversion is possible, and then intersystem crossing from S2 to T2. It is a straightforward transition. This is known as intersystem crossings, and of course another phenomenon is phosphorescence. So, the excited molecule can lose its energy by different phenomenon, still emit a radiation of longer wavelength. So, it is not just one phenomena that is involved in fluorescence, but it is several other phenomena that are involved in the loss of energy of the excited molecules. So, look at it. So, we will take a look at each of these phenomena in a little more detail. So, my next slide will show you that in fluorescence emission, transition always occurs from the lowest energy state, vibrational energy level, to the excited electronic state. However, during molecular electronic transition excitation, a molecule may be promoted to any of the vibrational states. So, excess energy than the lowest excited energy will be lost by collisions between the molecules and the solvent, that is excited molecules and the solvent. The energy transfer is obviously accompanied by a minuscule increase in the temperature of the solvent, and this phenomenon is also observed in spectrophotometry. There also excess energy, absorbed energy is released as heat, but the energy is so small that it almost goes unnoticed, but that is the only mechanism that happens in absorbance. But in fluorescence, it is one of the processes. Part of the energy is lost through absorption, and the temperature increase will be there. As a result, several closely spaced emission lines are produced, which may or may not appear in the fluorescence spectrum. As a consequence, what happens is the efficiency of the vibrational relaxation decreases. So, the fluorescence band gets shifted to longer wavelengths. So, another phenomenon that you should understand is internal conversions. Internal conversions is a crossover between two states of the same multiplicity, as in singlet state, that is one singlet state to another singlet state transition is possible, or triplet transition is also possible. So, they can intersystem crossings can also occur between S2 to S1 or S1 to S2, S0. So, usually these conversions are accompanied by a series of vibrational relaxations, as we have already seen, followed by intersystem. But that means there will be a quantum jump from the lowest vibrational energy to the triplet state. Therefore, whatever is the emission wavelength, fluorescence always will occur only at the longer wavelength. So, you need, if you are scanning a substance which is having a fluorescence property, you to look for the emission spectrum or emission peak, you need not go to lower wavelengths, but only go to the higher wavelengths. So, this is how an excitation and emission spectra occurs. This is for the molecule known as quinine, and here you can see I have plotted relative intensity versus wavelength, and this the blue line is the excitation wavelength, that is the radiation that is falling on the molecule, and the peak wavelength is approximately somewhere around 240 or something like that. And then there are other wavelengths, there is one here and one here, but that is not very important, because if you look at the emission wavelength, it starts from about 350. Okay. This is very special case, somewhere around 375, the excitation is around 200. That means you should use a UV lamp for this, for exciting the quinone molecule, and if it is starts if the peak is somewhere around 450, the emission you need one more monochromator to go to emission to this emission wavelength maxima, that is around 450. Okay, maybe slightly around 460 or so, but still you can see that the emission spectrum is having a single peak, and it is much smoother than this, but it is not always so. You should remember that even the emitted radiation spectrum can be quite complex depending upon the structure of the molecule and the amount and the intensity of this radiation that we are subjecting it to. Okay. So, internal conversion sometimes also results in pre-dissociation. You see, any energy transfer sometimes can cause dissociation also. So, the here the electron moves from a higher electronic state to an upper vibrational state of a lower electronic state. That means, we are talking of two electronic states, higher and upper, but different vibrational energies of the corresponding energies. So, the vibrational energy would be quite sufficient to rupture some weak bonds in the chromophore. So, dissociation processes normally reduce the fluorescence intensity because part of the molecule is destroyed anyway. So, the concentration of the substance becomes very less. So, we do not want dissociation processes. So, how do these dissociation processes take place basically? That is by supplying the higher energy. So, instead of 250 in the previous scale, in the previous slide, instead of 250, if I do this excitation around 350 or 375, then I can reduce the dissociation of the molecule and get a higher intensity of the emission spectrum. Okay. So, that is one of the decisions you will have to take whenever you want to do research on molecules regarding the fluorescence phenomenon. So, sometimes this deactivation what we talked of so far also involves interaction and energy transfer between the excited molecule and the solvent molecules. Solvent molecule can be aqueous solution, the water molecules, or it may be some other solute, it may be organic solvents like butane, like butanol, benzene, toluene, xylene, etc. So, the solute molecules, solvent molecules also can contribute to this deactivation. So, whenever a substance loses its energy by some interaction with some other molecules, not of its own molecule, then it is known as external conversion. So, this is important because it means that different solvent molecules, different if I take butanol, fluorescence intensity will be different compared to methanol or benzene or toluene or something like that. Okay. So, the medium becomes very important in the measurement of fluorescence also. So, the mechanism of such conversions are really not very well understood even now. So, now I come to the intersystem crossing. So, this is another way of loss of energy. Singlet to triplet transitions occur if there is any overlap of the electronic states of different multiplicities. You remember I had taught you multiplicities of the spectral lines in the initial stages when I was teaching you about the electronic structure of the atoms and molecules. So, you may refer to them again, and intersystem crossing is basically more common in molecules containing heavy atoms such as iodine, bromine, etc., where the spin and orbital interactions are very prominent. So, the fluorescence, you can check the fluorescence of any substance involving iodine. Normally it will show you a fluorescence even if you replace iodine with bromine, but the orbital interactions would be different because the structure, electronic structure of iodine and bromine are different. Iodine is having more electrons, higher number of higher molecular weight and atomic weight compared to bromine. So, the orbital interactions will be much more and more complex also. So, the presence of molecular oxygen is another factor that also enhances intersystem crossing with a consequent decrease in fluorescence. So, the more complicated interactions, the more decrease will be the fluorescence intensity. So, now I come to the phenomenon of phosphorescence, and after intersystem crossing from triplet to singlet state, the internal and external conversions also may take place, resulting in decreased fluorescence. This kind of emission is more common in highly viscous media at low temperatures. Okay. So, this I have explained to you yesterday or day before yesterday, where we can stabilize a system using polyvinyl alcohol, glycerol, glycerine and starch, dextrin, maltose, etc. And wherever such substances are there, the emission gets reduced, that means fluorescence gets reduced drastically. So, one has to be very careful if you want to apply the system for monitoring of a substance, you should know whether there are such substances like polyvinyl alcohol and some other chemicals which are having an influence of reducing the fluorescence phenomena. Okay. So, we come to the basics of fluorescence, and these are the transition types. It rarely occurs from emission radiation of more than 250 nanometer, because below 250 nanometers or even 180 nanometers, the property of the electromagnetic radiation is to dissociate and destroy the molecules, molecular bonds, etc. So, obviously it stands to reason that at very short wavelengths fluorescence phenomena does not occur. So, even if it occurs, it will be overshadowed by the by decomposition rather than fluorescence system to occur. Okay. So, the dissociation processes normally overtake the deactivate the excited states. Since most of the organic bonds are ruptured below 200, again fluorescence cannot occur due to sigma star to sigma transitions. See, I am talking about sigma star to sigma transitions. In absorbance, we used to talk of sigma to sigma star transitions. Now, in fluorescence, we are talking from higher energy level to lower energy level. So, sigma star to sigma transitions are normally not expected to produce any kind of fluorescence. Therefore, we can surmise that fluorescence normally occurs from pi star to pi, yes, definitely, and pi star to n transition still possible. Among these, the probability of fluorescence is more with respect to pi star to pi transitions. Okay. So, molar absorptivity of pi to pi star transitions are approximately 100 to 1000 fold greater than n to pi star transitions. The inherent lifetime associated with pi to pi star transition are also of the order of about 10 raised to minus 7 to 10 raised to minus 9 seconds, of course. So, compared with 10 raised to minus 5 to 10 raised to minus 7 seconds for n to pi star transitions. So, which is better? Among the two, 10 raised to minus 7 to 10 raised to minus 9 seconds is a longer wavelength, longer time limit for fluorescence to occur. So, obviously, pi star to pi transitions are most comfortable to work with, and they will be more stable also, 100 times at least. 10 raised to minus 7 to 10 raised to minus 9 means 100 times more stable. So, the most efficient phosphorescence, now we are talking of phosphorescence, this occurs from n to pi star excited states, which tends to be very short lived. Therefore, it is less susceptible to deactivation than pi to pi star transition state. In such systems, what happens is intersystem crossing is also very less, because the energy difference between the singlet and triplet state is quite large and spin orbit coupling is likely. So, spin orbit coupling likely means loss of fluorescence. So, is there a correlation between fluorescence and structure of the molecules? So, in general, with the discussion so far we had, we can conclude that n to pi star transitions are not suitable, because they sigma to sigma star transitions are not suitable for fluorescence, but pi to pi star transitions are more suitable. Therefore, if a system, a molecule is having number of bonds which are having pi to pi, number of pi bonds, then fluorescence can occur. We do not say it will occur, but it can occur. So, aliphatic and alicyclic carbonyl structures with conjugated double bonds, you remember we had discussed about such things when we were doing the prediction of the absorption wavelength depending upon the molecular structure in the absorbance. So, aliphatic and alicyclic carbonyl structures with conjugated double bonds, wherever there is conjugation we normally expect fluorescence. Of course, absorption will always be there, but fluorescence also may occur. So, a majority of the unsubstituted aromatic hydrocarbons, simple heterocyclic systems, they do not fluoresce in solution. So, even though there are double bonds, pi bonds. So, examples include in this slide I have shown you, that is pyridine, furan, there are conjugated double bonds here. There is a conjugated double bond in pyridine, that is nitrogen is here, and this is thiophene and pyrrole, and all these things do not fluorescence in the aqueous solutions.